Welcome to today's session. In this video, we'll dive into problem number 737, titled Sentence Similarity 2. This problem challenges us to determine if two sentences are similar based on given word relationships. We'll explore different approaches, analyze their complexities, and break down the solution step by step. Let's get started. In this problem, you are tasked with determining whether two sentences, represented as lists of strings, are similar based on a given set of word pairs. These word pairs, provided in a 2D array called similar pairs, define the similarity relationship between two words. A word is considered similar to a word B in three cases: if they are exactly the same, if they are directly listed as similar in similar pairs, or if there is a transitive chain of similarities connecting them. For example, if A is similar to C and C is similar to B, then A is also similar to B. The goal is to return true if all corresponding words in the two sentences are similar, and false otherwise. The output for this problem is a Boolean value. You will return true if the two sentences are similar under the defined rules, and false if they are not. Let's look at an example. Suppose we have two sentences. Sentence 1 is great, acting, skills, and sentence 2 as fine, drama, talent. The similar pairs array contains word pairs like great, good, fine, good, acting, drama, and skills, talent. Based on these pairs, we need to determine if the sentences are similar. In this example, the first words, great and fine, are similar because great is similar to good and fine is also similar to good, forming a transitive relationship. The second words, acting and drama, are directly similar as listed in similar pairs. Similarly, the third words, skills and talent, are directly similar. Since all corresponding words in the two sentences are similar, the output is true. Now consider another example where sentence 1 is great and sentence 2 is good, with similar pairs being empty. Here, there is no direct or transitive relationship between great and good, so the output is false. In the third example, sentence 1 is great, acting, and sentence 2 is great. The similar pairs array includes great, good, and acting, drama. While there are defined similarities, the two sentences have different lengths, which violates the requirement for sentence similarity. Both sentences must contain the same number of words to be considered similar. Therefore, in this case, the output is false. This highlights that sentence length is the first condition to check before evaluating word similarities. Finally, let's go over the constraints and edge cases. The lengths of both sentences are between 1 and 1000, while the similar pairs array can have up to 2000 pairs. Each word in the input has a length between 1 and 20 and consists of lowercase English letters. The similarity relationship is both transitive and symmetric, meaning if A is similar to B, then B is also similar to A. Some important edge cases include handling sentences of different lengths, which should immediately return false, and scenarios where similar pairs is empty. In such cases, only exact word matches are considered. Additionally, transitive chains of similarity require careful handling, which can be efficiently managed using union find or graph traversal techniques. To begin, one straightforward approach we might consider is the brute force method, which involves checking similarity word by word. The main idea here is simple. For every word in the first sentence, compare it to the corresponding word in the second sentence to determine if they are either directly or transitively similar. We iterate through the sentences, and for each pair of words at the same position, we first check if the words are identical. If not, we look through the similar pairs list to see if there's a direct or transitive relationship between them. Should we find any pair that fails this similarity check, the function immediately returns false? While this approach is conceptually simple, its inefficiency becomes apparent as the size of the sentences or the number of similarity pairs grows. The repeated traversal of similar pairs makes the time complexity O, n asterisk m, where n is the length of the sentences and m is the size of the similarity list. Thus, this method is not scalable for larger inputs, making it impractical for real-world applications. A more efficient solution leverages the union find data structure, also known as disjoint set union. The key insight here is to group similar words into connected components, where words within the same component are considered similar. This eliminates the need for repeated comparisons by pre-computing relationships. The transitive property of similarity plays a crucial role. If one word is similar to another, and that second word is similar to a third, then the first and third words are also similar. Using union find, we treat each word as a node, and every similarity pair connects two nodes. By unioning similar words into the same component, we can efficiently check if two words belong to the same group. When iterating through the sentences, we only need to check if the words are identical or if they share the same component using the find operation. This approach significantly reduces redundancy compared to brute force. The time complexity is O, m log k plus n log k, where m is the size of similar pairs, k is the number of unique words, and n is the sentence length. The space complexity is O, k, for maintaining the union find structure. This balance of efficiency and scalability makes union find a strong candidate for solving the problem. Another approach worth considering is graph-based, where we represent words as nodes and similarities as edges. This transforms the problem into a graph traversal task. The idea is to build an adjacency list from the similar pairs list, creating a graph where connected nodes signify similar words. To check similarity between two words, we either verify if they are identical or perform a depth-first search, DFS, starting from the first word to see if the second word is reachable through the graph. If no path exists, the function returns false. While this method effectively captures transitive relationships, its efficiency depends on the graph structure. The time complexity is O, n asterisk, k plus m, where n is the length of the sentences, k is the number of unique words, and m is the number of similarity pairs. The space complexity is O, k plus m, accounting for the adjacency list. Although intuitive, this method can be less efficient than union find due to the potential for repeated graph traversals during DFS, especially in dense graphs or large datasets. Ultimately, the union find approach emerges as the most efficient and practical choice. It excels at handling transitive relationships and avoids the redundant checks that hinder the brute force and graph-based methods. The key realization here is that similarity forms a connected components problem, which is precisely what union find is designed to solve. With its amortized O(1) operations for both find and union find is faster than graph-based DFS for determining component membership. While the brute force approach is simpler to implement, its inefficiency on larger inputs makes it unsuitable for real-world applications. By leveraging union find, we achieve an optimal balance between simplicity and scalability, making our solution robust even for large datasets and complex similarity chains. To solve the sentence similarity 2 problem, the first step is to clearly define the goal. We aim to determine if two sentences, sentence 1 and sentence 2, are similar based on a list of similar pairs. Two words are considered similar either if they are directly listed as a pair in similar pairs or if they are connected transitively through other pairs. With this understanding, the algorithm begins with input validation. This is crucial because if the lengths of the two sentences differ, they cannot be compared, and we can immediately return false. Next, we construct a graph representation of the similarity pairs to efficiently check both direct and transitive relationships. Here, a graph is represented as an adjacency list using a defaultIct. By iterating over each pair in similar pairs, we populate the graph such that for a pair, word 1, word 2 is added to the adjacency list of word 1 and vice versa. For example, with similar pairs containing pairs like great, good, fine, and fine, excellent, the graph maps great to good to both great and fine, and so on. This graph structure lays the foundation for the next steps in the algorithm. Once we have the graph representation, the next step is to compare the sentences word by word. This ensures that each pair of corresponding words in the two sentences is either identical or similar based on the graph. Using Python's zip function, we can iterate through both sentences in parallel. For each pair of words, if the words are identical, we simply move to the next pair. However, if the words differ, we check their similarity by determining if they are connected in the graph, either directly or transitively. To handle transitive similarity, we use a graph traversal technique like breadth-first search or depth-first search. Starting from one word, we explore its neighbors in the graph to see if the other word can be reached. A visited set is used during this traversal to prevent cycles and avoid redundant processing. If the second word is found during this traversal, the words are considered similar, otherwise, they are not. After processing all word pairs, if every pair is found to be similar, we return true. Otherwise, we return false, indicating that the sentences are not similar. The algorithm is built on several key insights that enhance its efficiency and clarity. Representing the similar pairs as a graph is particularly powerful, as it allows us to efficiently handle both direct and transitive similarity checks. By using an adjacency list, we ensure that graph traversal is straightforward and scalable. Additionally, early termination is an important optimization. For example, if the sentences differ in length or if we encounter a dissimilar word pair, we can immediately conclude that the sentences are not similar and avoid unnecessary computations. For transitive similarity, BFS or DFS is used to explore complex chains of connections, such as great leading to good, then to fine, and finally to excellent. Handling edge cases is also critical. For instance, if both sentences consist of identical words or if no similarity pairs are provided, the algorithm still behaves predictably. Data structures play a vital role here as well. The default dict efficiently manages the adjacency list, while the visited set ensures that graph traversals are cycle-free and optimized for performance. Finally, let's analyze the computational complexity of the algorithm. Constructing the graph from similar pairs has a time complexity of O, P, where P is the number of pairs. For the similarity check, let N represent the number of words in each sentence and M the average size of the adjacency list. Each graph traversal, whether using BFS or DFS, takes O, M, time per word pair, resulting in a total complexity of O, N asterisk M, for the sentence comparison. This ensures the algorithm scales well for moderately sized inputs. To optimize further, iterative DFS can be used to avoid recursion stack limits, which is especially useful for large graphs. Another powerful optimization involves pre-computing connected components of the graph using a union-find data structure. By doing this, we can determine similarity between any two words in constant time, significantly improving performance for repeated queries. These techniques ensure that the algorithm is not only correct but also efficient and robust for various input scenarios. To solve the problem, we start by importing the necessary libraries. Here, we use default dict for creating the adjacency list and deque for implementing a queue in our breadth-first search. We then define the rSentencesSimilar2 method within a class called solution. The first thing we check is whether the lengths of the two sentences are the same, because if they differ, the sentences cannot be similar and we directly return false. Next, we construct a graph to represent the similarity relationships between words, using an adjacency list. For each pair of similar words in the input list, we add an edge in both directions, ensuring that the graph remains undirected. This allows us to easily traverse between all words connected through similarity relationships. We then define a helper function called BFS, which will be responsible for determining whether two words are connected within this graph. The function starts by initializing a queue with the first word and is set to track visited nodes. The first word is marked as visited to avoid revisiting it during traversal. The breadth-first search proceeds by dequeuing elements and checking their neighbors. If the target word is found, the function immediately returns true, indicating a connection. Otherwise, unvisited neighbors are added to the queue, ensuring all reachable nodes are explored. The BFS function continues by returning false if the target word is not found after exploring all possible paths. Now, with the helper function in place, we move on to checking the two sentences word by word. Using the zip function, we iterate through pairs of words from sentence 1 and sentence 2. If the words at a given position are identical, we consider them similar and move on. However, if they are different, we call the BFS function to determine if the two words are connected in the similarity graph. If BFS returns false for any pair of words, it means the sentences are not similar, and we return false immediately. Finally, if all word pairs pass the similarity check, the function concludes by returning true, indicating that the two sentences are similar. This implementation ensures correctness by leveraging graph traversal and efficiently handles the problem constraints. Here, we begin by importing the necessary classes and defining our solution. The method rSentencesSimilar2 takes two sentences, represented as arrays of strings, and a list of similar word pairs. The first thing we check is whether the lengths of the two sentences are equal. If they're not, we can immediately return false because sentences of different lengths cannot be similar. Next, we construct an adjacency list to represent the similarity graph. This graph will map each word to a list of words it is directly similar to. For each pair in the given list of similar pairs, we establish bidirectional connections by adding each word to the other's adjacency list. This adjacency list will allow us to traverse through the graph and determine connectivity between words. Finally, we define a helper function BFS to perform a breadth-first search, which will be used to check whether two words are connected within the graph. The BFS function is implemented to determine if there's a path between two words in the similarity graph. We start by checking if the first word even exists in the graph. If it doesn't, we return false immediately. Otherwise, we initialize a queue for the BFS traversal and a set to track visited nodes. The first word is added to both the queue and the visited set. Inside the while loop, we process each word in the queue. If the current word matches the target word, we return true, as this means the two words are connected. Otherwise, we look at all the neighbors of the current word in the graph. For any neighbor that hasn't been visited yet, we mark it as visited and enqueue it for further exploration. If the loop completes without finding the target word, we return false, indicating no connection exists. After defining the BFS function, we loop through the words in both sentences. For each pair of words at the same index, we check if they are identical. If not, we use the BFS function to check if they are connected in the graph. If neither condition is met, the sentences cannot be similar, so we return false. If we get through all the pairs successfully, we return true, confirming the sentences are similar. Finally, we close the class definition. The implementation is complete, encapsulating the logic for comparing sentence similarity using a graph-based approach and breadth-first search to determine connectivity. This solution effectively handles the problem constraints and ensures that the similarity relationships between words are thoroughly checked. In this first example, we are tasked with determining whether two sentences, sentence 1 and sentence 2, are similar based on the given pairs of similar words. The input sentences are great acting skills and fine drama talent, and the similar pairs establish relationships between certain words. The first step in solving this is to compare the lengths of the sentences. Both sentences have a length of 3, so we proceed. Next, we construct a graph to represent the similarity relationships. Initially, the graph is empty. As we process each pair, we add bidirectional edges. For instance, the pair great and fine is added, and the graph updates accordingly. Repeating this for all pairs, we end up with a graph where great is connected to fine, drama is connected to acting, and skills is connected to talent. This graph will allow us to explore relationships between words efficiently. Now that the graph is built, we proceed to compare each pair of corresponding words from the two sentences. Starting with great and fine, we use a breadth-first search to explore their connection. Beginning at great, we initialize the queue and visited set. After dequeuing great, we explore its neighbors and find fine, confirming a similarity. The process repeats for the next pair, acting and drama, where BFS starts at acting. Again, we explore its neighbors and find drama, returning true. Finally, for skills and talent, BFS starts at skills, and we find talent in its neighbors. All comparisons result in true, so we conclude that the sentences are similar, and the output is true. In this second example, we evaluate sentences that may not be similar. The input sentences are great skills and fine cooking, and the similar pairs include relationships between great and fine as well as skills and talent. After confirming the sentences have the same length, we build the graph. Starting with an empty graph, we add the pairs, creating connections between great and fine, and skills and talent. With the graph complete, we can now begin comparing corresponding words in the two sentences. The first comparison is between great and fine. Using BFS, we start at great, initialize the queue and visited set, and explore its neighbors. We find fine, confirming similarity. However, when comparing skills and cooking, BFS starts at skills, but no path leads to cooking. The graph does not connect skills to cooking, so we determine they are not similar. As a result, the sentences are not similar overall, and the output is false. In this third example, we explore transitive similarity, where connections span multiple pairs. The sentences are great skills and fine talent, with pairs establishing relationships such as great to good to fine, and skills to talent. After verifying the sentence lengths match, we build the graph. Starting from an empty graph, we add great and good, followed by good and fine, and finally skills and talent. This results in a graph where great connects indirectly to fine through good, illustrating transitive similarity. To compare the sentences, we first examine great and fine. BFS begins at great, exploring its neighbors. From great, we reach good and then continue to fine, confirming similarity. Next, we compare skills and talent. Starting BFS at skills, we quickly find talent as a direct neighbor. Both word pairs are similar, so the sentences are deemed similar overall. The output is true. To analyze the time complexity of the sentences similar to function, we start by breaking it down into its major components. First, we consider the time required to build the graph. This step involves processing the similar pairs list to construct an adjacency list representation of the graph. For each pair, W1, W2, in similar pairs, we perform two operations, appending W2 to the list of neighbors for W1 and appending W1 to the list of neighbors for W2. If there are P pairs in similar pairs, this process takes P time. Next, we analyze the BFS traversal, which is used to check connectivity between words. For every word pair, W1, W2, in sentence 1 and sentence 2, a BFS traversal is performed if the two words differ. Let n represent the number of words in sentence 1, which is the same as in sentence 2 since their lengths are equal. In the worst case, the BFS traversal might visit all nodes and edges in the graph. Assuming V is the total number of unique words across all pairs and E is the number of edges, each BFS call takes V plus E. Now, let's consider the time spent checking all word pairs. For each word pair, W1, W2, in sentence 1 and sentence 2, the BFS helper function is called. Since there are n word pairs in total, this means the BFS function is invoked n times. In the worst case, each BFS traversal involves visiting all nodes and edges in the graph. Therefore, the contribution of these calls to the overall time complexity is n*, V plus E. When we combine this with the graph construction time of P, the total time complexity of the function becomes P plus n*, V plus E. This accounts for both constructing the graph and performing the connectivity checks using BFS. Next, we analyze the space complexity of the solution, which is determined by several factors. First, we consider the adjacency list used to store the graph. Each edge, W1, W2, is stored twice, once for W1 and once for W2. This results in a total space usage of V plus E, where V is the number of unique words and E is the number of edges. Additionally, during BFS traversal, we use a queue to manage the nodes being visited and a set to track visited nodes. In the worst case, the queue and the visited set can each grow to a size of V, contributing V space each. Finally, other variables such as the input list sentence 1, sentence 2, and similar pairs do not contribute to extra space usage, as they are part of the input itself. Combining these factors, the overall space complexity is dominated by the adjacency list and the BFS data structures, leading to a total of V plus E. Now, summarizing the total space complexity, we see that the adjacency list requires V plus E space, while the BFS queue and the visited set require an additional V. This results in a total space complexity of V plus E. Comparing this graph-based approach to a naive method highlights the efficiency of the current solution. A naive approach would involve directly comparing all possible paths between W1 and W2 in the similar pairs list. This could require exploring all combinations of paths, resulting in an exponential time complexity of 2 to the power of p for p pairs, which is highly inefficient. In contrast, the graph-based approach improves efficiency by organizing relationships into an adjacency list for fast access and using BFS to ensure that each node and edge is visited at most once. This structured approach significantly reduces the complexity, making the solution much more scalable. Finally, let's discuss the best, average, and worst-case scenarios for this solution. In the best case, sentence 1 and sentence 2 are identical, meaning no BFS calls are needed. Here, the time complexity reduces to just the graph construction time of P. In the average case, some word pairs require BFS calls, leading to a time complexity of P plus n*, V plus E. The worst case occurs when every word pair requires a full BFS traversal of the graph, resulting again in O, P plus N asterisk, V plus E. To justify the big O notation mathematically, we note that graph construction involves iterating over all pairs, which is O, P. Each BFS traversal visits every node and edge at most once, which is O, V plus E. Since BFS is invoked n times 4n word pairs, the total contribution is O, N asterisk, V plus E. Combining these, the total time complexity is O, P plus N asterisk, V plus E. The space complexity follows from storing the adjacency list and using BFS data structures, leading to O, V plus E, overall. When solving sentence similarity 2, there are several common pitfalls to be aware of. The first is ignoring transitive relationships in the similarity graph. For example, if word A is similar to word B, and word B is similar to word C, then A should also be considered similar to C. Some solutions fail to account for this, leading to incorrect results when dealing with more complex networks of similarity. Next is inefficient graph traversal. If you're recalculating paths for every pair of words, this can significantly slow down your solution, especially for large inputs. A better approach is to pre-process the graph using techniques like union find or adjacency lists, which allow for faster and more efficient similarity checks. Another issue is misaligned sentence lengths. Assuming that the two input sentences are always the same length can result in runtime errors for edge cases. Always validate the input constraints to ensure your solution is robust. Additionally, edge cases like empty sentences, duplicate pairs in the similarity list, or handling self-similarity where a word should naturally be considered similar to itself can lead to unexpected behavior if not accounted for. Finally, incorrect implementation of union find is another frequent mistake. Forgetting optimizations like path compression or union by rank can lead to poor performance and incorrect groupings, which undermines the purpose of using union find in the first place. Now, let's dive into some key insights that can help you perform well in interviews for this problem. First, focus on how you represent the graph. This problem revolves around graph traversal and identifying connected components, so you should be ready to discuss the trade-offs between adjacency lists, adjacency matrices, and union find. For example, adjacency lists are space-efficient but require more effort during traversal, whereas union find is highly efficient but involves pre-processing. Next, optimize your solution for scalability. Highlight how your approach handles large datasets, such as when the number of similarity pairs or the sentence length grows significantly. Union find is particularly powerful here, with near constant time operations for union and find, making it an excellent choice for large inputs. Another important point is to clarify assumptions. For instance, is similarity always transitive? Can the input sentences be empty? Could the similarity pairs list contain duplicates? Explicitly verifying these details with the interviewer demonstrates thoroughness and clear communication. Lastly, testing with edge cases is vital. If you can proactively test your solution against potential tricky scenarios during a whiteboard interview, it shows robustness in your approach and critical thinking skills. To deepen your understanding, it's helpful to explore related problems that share similar concepts. For instance, the problem we're discussing, LeetCode 737, Sentence Similarity 2, directly focuses on transitive similarity and can be approached using union find or depth-first search. Another related problem is LeetCode 721, Accounts Merge, where the goal is to merge connected components within a graph structure, much like grouping similar words here. LeetCode 323, Number of connected components in an undirected graph, also emphasizes identifying connected components, which is a key skill for solving this problem effectively. Finally, LeetCode 399, Evaluate Division, involves graph traversal to calculate relationships, such as determining how two variables are connected through a series of equations. These problems all share the common thread of leveraging graph-based algorithms to solve real-world challenges, so practicing them can help reinforce the core concepts. Finally, let's consider some alternative approaches to solving this problem and their trade-offs. Union find is a highly efficient method for handling large inputs. By using path compression and union by rank, you can ensure quick union and find operations. However, it does require pre-processing time and additional space to store parent and rank arrays. Its complexity is approximately O, n plus m asterisk alpha, n, where n is the number of words and m is the number of similarity pairs. Depth first search, or DFS, is another option. It's often easier to implement but performs poorly when repeated similarity checks are required, as it explores all paths for each comparison. The complexity here can reach O and *m in the worst case. If simplicity is your priority, adjacency matrix representation is straightforward but comes at the cost of O n squared space, which is impractical for handling larger inputs. Lastly, brute force comparison is the least efficient approach. While it might work for very small inputs, its O and *m complexity makes it unsuitable for real-world scenarios. Choosing the right approach depends on input size, constraints, and the specific trade-offs you're willing to make. Great job following along. Today, we tackled problem number 737 and learned how to use graph traversal techniques like DFS or union find to determine sentence similarity. Remember, mastering graph-based problems is key for technical interviews. Thanks for watching, and don't forget to like, subscribe, and practice more problems. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!